Students, in this session we will discuss about Mach Zehnder interferometer multiplexers. And this multiplexer is worked on the basis of Mach Zehnder interferometer. So let us see what is MZI or Mach Zehnder interferometer. The MZI consists of two 100% reflective mirrors. It also consists to 50% reflective beam splitters. And also it contains a beam combiner. Let us see the diagram. See, this is a Mach Zehnder interferometer, and here there is an input beam and it will be splitted by a beam splitter, so that beams will be going to different paths where they are reflected by the 100% reflective mirrors. You can see these mirrors here, and due to this reflection the path of the two waves will be different, and these beams will be combined by a beam splitter. Here it is given that beam splitter, actually it is a combiner. The splitter can act as a combiner, and where they will be routed to different path. Okay, that's the principle of MZI. And the input beam is split into two parts. These two beams travel different paths through the interferometer, and beam in one path is phase shifted with respect to the beam in the other path. When these beams combine, they cause constructive or destructive interference. The phase shift to one of the beam paths serves as an amplitude modulator and controls the output signal from the device. And here, when the beam is reflected from these mirrors, that is 100% reflective mirrors, they undergo a phase shift, and due to this phase shift, when they are combined by the combiner, the interference, that is constructive or destructive interference, that depends upon the phase shift. Okay, so that is the principle of the interferometer, and we can construct a Mach Zehnder interferometer multiplexer by using this. That means wavelength dependent multiplexers can be made using the Mach Zehnder interferometer techniques, and figure shows the constituents of the Mach Zehnder interferometer multiplexer. And here you can see that it represents a 2x2 MZI, that is 2x2 Mach Zehnder interferometer multiplexer. And here you can see that the inputs 2x2 means here there are two input lines and two output lines. Okay. See, it consists of three stages. That first stage is 3 dB splitter, and here you can see that it is given that 3 dB directional coupler. A coupler can act as a splitter as well as combiner. A 3 dB directional coupler, and that means here it is used for splitting the input signal to two different paths. Okay, and here inputs are coming from this path where they are combined here, and they will be given to two different paths. And also there is another, at the final stage there is another, at the output section there is another split 3 dB combiner where these two signals will be combined here, and it will be given to two different paths. Okay, and the central section you can see two different paths and which act as a waveguide, and here you can see that its length is L and other path length is L plus delta L. That means it represents a path difference. The central section where one of the waveguide is longer by delta L to give a wavelength dependent phase shift between the two arms. And this here the 3 dB combiner, which is also a coupler. See, coupler can act as a splitter as well as a combiner. Okay, so let us see the details. And the function of this arrangement is that by splitting the input beam and introducing a phase shift in one of the path, the recombined signal will interfere constructively at one output and destructive at the other. See, here the signals will be combined here, and they will be splitted at the output of this 3 dB splitter, and they will be given to two different paths where the path length is different, so that they will undergo a phase shift when traveling through this waveguide section, and then again they will be combined by this 3 dB combiner. So this path, so when they are combining, so the phase shifted signals are combined here, they may undergo constructive or destructive interfered. The result of the constructive interference will occur obtained from this channel, or from this path, and the result of the destructive interference is obtained from this channel. That is why two paths are marked here. Okay. So due to this interference, we will get only one signals. So the signals then finally emerge from only one output port. That means the result of the destructive interference is 0. That is why we are saying the signals then finally emerge from only one output port. And let us see the derivation side. The propagation matrix for this coupler. See here there are two couplers. One coupler here and one coupler here. And let us see the propagation matrix for the coupler of length D is given by, here the coupler length is, you can see here that D is the coupler length. So the propagation matrix for that coupler will be, M coupler will be equal to cos KD into J sin KD, J sin KD cos KD. This is the propagation matrix for the coupler. And here K is the coupling coefficients, and since we are considering a 3 dB coupler, that means the power will be divided equally to different path by this coupler. So we can say that 2 kd will be equal to pi by 2, so that kd will be equal to pi by 4. So when you are substituting that kd value here, you will get the M coupler will be equal to 1 by root 2 into 1 by root 2 matrix 1 j j and 1. That will be the matrix. Since cos kd, cos pi by 4 and sin pi by 4 values are 1 by root 2. So you can again see in the central region there is a small path difference, that is delta L is the path difference. Due to that path difference in this waveguide section of length L, there will be a phase difference for the signals emerging in that waveguide sections. So that phase difference may be delta phi. We are assuming that that phase difference is delta phi. That is delta phi is given by 2 pi n1 by lambda into L minus 2 pi n2 by lambda into L plus delta L. So this phase difference is the difference between the phases of the signals passing through the one waveguide to the other waveguide. You can see that one waveguide path has a length L and other waveguide path has a length L plus delta L. So the difference will be this one. You can see that here one term will be cancelled out when both the refractive indices are same. See here phase difference occur due to two factors. One is due to the path difference and other is due to the difference in the refractive index. And here the refractive index of path having length L is N1 and the refractive index of path having length L plus delta is N2. If both of the refractive indices are same, that means N1 equal to N2 is equal to N effective, then we can substitute that value here so that the common terms will be cancelled out. So you will get delta phi will be equal to 2 pi N effective by lambda into delta L. So delta phi you can write it as K into delta L, where K is equal to 2 pi N effective by L lambda. So for a particular phase difference delta phi, when it is propagated through that waveguide section, the propagation matrix for that phase shifter portion, that is the waves is propagating through this path, through this waveguide section. So there will be some phase difference associated with this and this one. And when the refractive indices are same, the phase difference is delta phi is equal to K into LA. When that wave is propagating through this path, then the corresponding matrix for this path is given by propagation matrix corresponding to that phase difference delta phi is given by M delta phi is equal to e raised to j k delta L by 2 0 0 e raised to minus j k delta L by 2. That is the propagation matrix corresponding to the waveguide path. That is corresponding to the phase difference delta phi. So we will have, you know that we will have now 3 sections, that is this 2 coupler sections and 1 waveguide sections. So we will have different matrices, that is M delta phi and M phi. M phi is M coupler. Okay. So we are having input E in 1 and E in 2 and output E out 1 and E out 2. That is obtained from this figure. You can E out 1 and E out 2 are the output and E in 1 and E in 2 are the input. So we can represent this E in 1 and E in 2 and the product of this matrix will be equal to the output. So you can write the output will be equal to E out1 by E out2 equal to M into E in1 by E into. So where M will be is the product of M coupler, there will be two couplers, so M coupler into M delta phi. M delta phi is the phase difference associated with the waveguide. So that matrix is equal to M11, M21, M12 and M22. That will be equal to J into sin K delta L by 2 into cos K delta L by 2, cos K delta L by 2 minus sin K delta L by 2. When you are multiplying these two signals, that means this coupler matrix and this input signal, so you will get output. Since we want to build our aim is to build a multiplexer, we need to have the inputs to MZI at a different wavelength. See here, we want to construct a multiplexer from the MZI, that is Mach Zehnder interferometer. We want to construct a multiplexer. So we have to say that one input is associated with one particular wavelength and other input is associated with the other particular wavelength. Let E in 1 is associated with lambda 1 and E in 2 is associated with lambda 2. So since we want to build a multiplexer, we need to have the input to the MZI at a different wavelength, that is E in 1 is at lambda 1 and E in 2 is at lambda 2. Therefore, the output by the above matrix is equal to, we have the previous, in the previous case we have, this is the output, so we can multiply M with that E in 1. So you will get the E out will be equal to, E out 1 will be equal to J into E in 1 at wavelength lambda 1 into the matrix entries are multiplied, so you will get sin K1 delta L by 2 plus E into which is at lambda 2, it is multiplied by cos K2 delta L by 2. Similarly, E out 2 will be equal to J into E in 1 of lambda 1 cos K1 delta L by 2 minus E into lambda 2 sin K2 delta L by 2. So these are the output amplitudes. So in order to find the output powers, it is found from the light intensity, that is from the upper terms, and which is the square of the field strength, that is P out will be equal to E out 1 into E conjugate out 1. So you will get a sin square K1 delta L by 2 P in 1 plus cos square K2 delta L by 2 P into. Similarly, P out 2 will be equal to E out 2 into E conjugate out 2. When you are multiplying those two, you will get a cos square K1 delta L by 2 P in 1 plus sin square K2 delta L by 2 P into. If we want all the powers from both the inputs to leave the same output port, then it should satisfy the condition K1 minus K2 into delta L equal to 2 pi n effective into 1 by lambda 1 minus 1 by lambda 2 into delta L, which is equal to pi. So this is the condition for the Mach Zehnder interferometer to act as a multiplexer. So K1 minus K2 into delta L should be equal to pi. And the length difference in the interferometer arms should be delta L will be equal to C by 2 n effective delta V, where delta V is the frequency separation of the two arms. So in order to act this Mach Zehnder interferometer as a multiplexer, it should satisfy the condition, that is delta L will be equal to C by 2 n effective into delta V, where delta V is the frequency separation of the two wavelengths, that is lambda 1 and lambda 2. And delta L is the path difference between the two paths. Okay. Similarly, by using the same 2 by 2 MZI, that is Mach Zehnder interferometer, we can construct an n by n multiplexer. So the connection is like this. Here we will use one 2 by 2 Mach Zehnder interferometer and another Mach Zehnder interferometer, and the output here it will have two output, and here also it will have two output, and that output will be combined by another Mach Zehnder interferometer MZ3. So it will give a 4 output. Okay, that is, here you can see the inputs are in this 2 by 2 Mach Zehnder interferometer, the input frequencies V and or nu and nu plus 2 delta nu. That is a frequency difference of delta nu. Okay, sorry, 2 delta nu here, and it is associated with the wavelength lambda 1 and lambda 3. Similarly, in the second MZI, and here the wavelength is lambda 2 and lambda 3, and you can see here that here the input is nu plus delta nu and nu plus 3 delta nu, and the output is obtained here is this one, and here it is given to another Mach Zehnder interferometer and the output is taken here. So from the 2 by 2 MZI you can construct n by n multiplexer like that, and here in the figure a 4 by 4 multiplexer is shown, and here input to MZI1 are nu and here it is indicated as V and V plus 2 delta V, and the input to MZI2 are V plus delta V and V plus 3 delta V. And in the first stage inputs are separated by 2 delta V, so path difference should satisfy the condition delta L1 equal to delta L2 equal to C by 2 n effective into 2 delta V. In the second stage the inputs are separated by delta V, and correspondingly it should satisfy the condition delta L3 is equal to C by 2 n effective into delta V, that is equal to 2 delta L1. So this is the condition for the multiplexer by using the MZI. Okay. So similarly we can use the same multiplexer as a demultiplexer also. So an n to 1 MZI multiplexer can also be used as a 1 by n demultiplexer. That's all about this topic. Thank you.